Here are my 5 tips you need to know before you start working with ESP32-C3 Super Mini microcontroller. And don't miss the last one, where I pull 2 extra GPIO pins out of the thin air. Are you intrigued? Stick around.
Tip number 1. Serial monitor. Dead or just misconfigured?
Let's start with something simple and straightforward. This is our ESP32-C3 Super Mini microcontroller, mounted on a breadboard and connected to the PC using the USB interface. After installing the ESP32 family package in the Arduino IDE, we can select the ESP32-C3 board. Here is a super simple sketch. In setup, it just opens the serial connection and prints a simple message, so we can confirm that the serial monitor is working. Before uploading the code, let's open the serial monitor and make sure the baud rate defined in the sketch matches the baud rate selected in the serial monitor. The code compiles. The upload starts and completes successfully. And nothing appears in the serial monitor. That's not good. So what can we do? If you open the settings for this particular ESP board, you will see an option for serial communication over USB. It is disabled by default. Let's enable it. This time I would expect the serial monitor to behave differently. And I was wrong. Still, nothing is displayed. Yeah, this looks a bit silly now. Any idea what the problem could be? I'll give you 5 seconds to think about it. Did you come up with anything? The solution is actually quite simple. The serial monitor, like anything in life, needs a little time to get itself ready. In our code, we are printing to serial immediately after opening it. Let's give it 1 second to properly initialize. Now let's upload the code again. And this time, it works. First tip down, 4 to go.
Tip number 2. Why is my LED freaking out?
I came across this second tip while working with a different flavor of ESP32-C3 microcontroller, the version with a built-in OLED display. Let's first set the stage for explaining this tip. Since the Super Mini ESP32-C3 does not have a built-in OLED display, I added an external one to the breadboard setup. As you can see, it's already powered from the 3.3 volt and ground pins. Because this is the I2C device, we also need to connect the data and clock lines. According to the pinout for this board, GPIO pin 8 is used as a data pin and GPIO 9 is used as the clock pin. I'm not going to write the OLED code from scratch. Instead, I will open one of the example sketches that came with the OLED display library. There is just one small change we need to make. OLED displays of this kind have a predefined I2C address, and there are usually 2 possible values, 3C and 3D. The example sketch is configured for 3D, but my display uses 3C, so let's change that. Now we can test the code. It's compiling. The upload is finishing and the OLED display demo starts. And it looks great, but we are not here to admire the graphics. We are here to look at this LED blinking like crazy. Why is that happening? The reason is that this LED is connected to GPIO pin 8, which also happens to be default I2C data pin. I don't know about you, but this blinking really annoys me. Not to mention that in a battery-powered project, it's a completely unnecessary waste of power. So what can we do about it? Fortunately, the ESP gives us a lot of flexibility and we can easily reassign the I2C pins. Let's move the data line to GPIO pin 5 and the clock line to the GPIO pin 6. When we power up the microcontroller now, the OLED demo is no longer displayed, because the display is no longer connected to the active I2C bus. Before uploading the code again, we need to update it. By calling wire begin with the new data and clock pin numbers, we reinitialize the I2C on the new pins. Now let's upload the code again. And there it is! The demo is back on the OLED display. And most importantly, the annoying LED blinking is gone. How about that? The sponsor of this video is PCBWay, a premier manufacturer of printed circuit boards. If you want to take your projects to the next level, just like I did with the custom PCB used to build this cool looking 7-segment NeoPixel display, from early prototype to finished design, they help you to turn your ideas into high quality real world projects. To get started, just click at the link at the top of the screen.
Tip number 3. The Wi-Fi that refused to connect.
The tip number 3 is probably the most consequential of all 5 because it deals with Wi-Fi connectivity. But first things first, let's explain what the issue is. When I bought this module, I was amazed by how compact it is and how much functionality it offers. I designed a universal NeoPixel LED controller, and the sponsor of this video, PCBWay, helped me bring this design to life. However, before I could even use it in any real project, I realized that this board failed to connect to Wi-Fi, which would have completely killed the entire idea. Let's demonstrate this problem with a simple sketch that uses my hotspot credentials to connect the microcontroller to the network, and then, once the connection is successful, display the IP address assigned to it by the router. Let's load this code and see if we can connect to the Wi-Fi. Before we start, I will open the serial monitor so we can observe the results. The code is now loaded, and as you can see, the microcontroller is constantly trying to connect, but with no luck. So let's break down the problem. Issues with Wi-Fi connectivity are usually caused by one of 3 things. Problems with antenna, either due to hardware design flaws or physical interference, an unstable power supply, or software settings such as excessively high transmit power. In my case, the power supply was solid, and I didn't see any interfering with the antenna. So the next thing to try was adjusting the Wi-Fi transmit power. The default transmit power is 20.5 dBm. Let's reduce it to the minimum value, which is 8.5 dBm. What does this mean for our project? On the positive side, it improves connection stability and lowers current consumption, which is great news. The downside is that the wireless range becomes smaller, but for local networks this usually doesn't matter. So how do we actually make this change? It can be done with a single command in the code, like this one. That's the theory. Now let's add this line to the code and see if it makes any difference. The code is loading. The sketch attempts to connect to Wi-Fi, and this time it's successful. We can see the assigned IP address, which confirms that the connection worked. With just one line of code, my project is saved.
Tip number 4. When the USB says nope.
The 4th tip does not apply to the microcontroller I have, but when I was ordering it, I did some research beforehand, and I was certain I would not be able to upload code using USB cable. Several forum posts claimed that I would have to upload code using UART adapter, like this one. That didn't scare me because I had done similar routine before when working with Arduino Pro Mini. But when the board arrived, to my surprise, uploading via USB cable worked perfectly. However, if you're less lucky than I was, and you order an ESP32-C3 Mini that does not support USB uploads, you can still load the code using UART adapter. To test it, I will use a simple blink sketch. I added an LED to the breadboard and connected it to GPIO pin 5. The UART adapter has clearly marked pins we need to connect. Ground to ground, 3.3 volt pin to the 3.3 volt pin of the microcontroller. Very important, do not connect 5 volts as this could damage the board. Then you cross serial pins. TX goes to RX and RX goes to TX. For this board, RX is on GPIO pin 20 and TX is on GPIO pin 21. Let's connect UART adapter. Connecting ground, 3.3 volt, pin 20, and finally pin 21. Next, let's connect the adapter to the PC and check if the serial port appears in Arduino IDE. It does, So let's begin the upload. And it does not work. You can see the PC trying to establish the connection for a while, and eventually an error message is displayed. On the Arduino Pro Mini, you had to press the boot button at the moment the upload starts. But I tried that here, and it did not work. In one of the forum posts, I found information that to put this microcontroller into programming mode, you need to short pin 9 to ground. So let's do that. Done. Now let's repeat the upload. Still no luck. I dug a bit deeper and traced the problem to the upload speed setting in the Arduino IDE. By default, it was set to the maximum value, which is too fast for the UART uploads. Let's change this setting to a lower value and try uploading the code one more time. And this time it works. Or does it? Although the code appears to have been uploaded successfully, the LED is not blinking. So what's wrong? To allow the code to run, we need to exit programming mode. We do this by disconnecting digital pin 9 from ground. After reconnecting the board, the sketch runs as expected, and you can see the LED blinking. Wonderful! Now I know how to upload code to the microcontroller even if the USB-C port isn't working. If you find this method of uploading a nuisance, there is an easier approach. Upload a sketch via UART once that enables over-the-air OTA updates. After that you can upload sketches over Wi-Fi, so you won't need the adapter anymore. If you're not familiar with OTA uploads, you may want to check out this video of mine.
Tip number 5. The GPIO Ninja move. Stealing pins 18 and 19 from USB.
As much as you may praise this little microcontroller, there's one limitation you can't overcome due to its compact size, and that is the number of pins. It's limited to begin with, and on top of that, some pins are reserved for special functions. So in some projects, you might find yourself 1 or 2 pins short, and there is nothing you can do about it. Or is there? While going through the microcontroller's documentation, I came across information that 2 GPIO pins are used by the USB-C connection. If we are not using USB for uploading code or serial communication, we can in theory reclaim those pins and use them for something else. At the beginning of this video, we were wondering why serial communication over USB is disabled by default in the Arduino IDE. Now we just found one of the reasons why. Ideally, we would use USB-C breakout board like this one. Unfortunately, I don't have one, so I will need to get a bit creative. I will use this USB-A female socket, which exposes the data pins. I will try to connect them to the positive and negative data pins of the USB-C connection of the microcontroller. The other 2 pins are VCC and ground, and I won't touch those. I will solder 2 DuPont female header pins onto the data pins of the USB-A socket, so we can test whether GPIO pins 18 and 19 can actually be used. And here is our little workaround. Definitely not ideal, but it will do. We don't need any complicated code to test this. I will continue using the blink sketch, but I will just change the LED pin from GPIO 5 to GPIO 18. Before we build a breadboard prototype for this test, let's first upload the blink code to the microcontroller using the USB cable. Now that the code is loaded, we can build the breadboard setup for testing. Here's our microcontroller. We also need a power supply module to power the breadboard rails. From those rails, we will power the board using 5 volt and ground pins. We will connect the LED to the negative power rail. Now we can connect the USB cable to the USB-C port of the microcontroller on one side and to the USB-A socket device we created earlier on the other. This way we expose GPIO pins 18 and 19. Then using a jumper wire we can connect GPIO pin 18 to the positive side of the LED. Now we are ready for testing. It will either work or something will go terribly wrong and I will destroy this board. When I started working on this video, I wasn't sure this would work. I left this test for the very end. Even while scripting the voiceover, I still didn't know the outcome. I decided to include this tip regardless of the final result because it's so cool. Then even if it failed, I wanted to show you this attempt. So with all that said, here is the moment of truth. And the LED is blinking. I won't show the same test for GPIO pin 19, but trust me, it works just as well. There's just one more thing to be aware of. By taking over the ESP32-C3 native USB pins, we temporarily disable its USB programming interface, so the port no longer appears when the board is connected to the PC. Don't worry, this is easy to fix. Disconnect the board, press and hold the boot button, and reconnect it to the PC. After a few seconds, release the button. The USB port will reappear in the IDE, and we can continue uploading code over USB-C. And that's it. Those are my 5 tips you need to know before you start working with that microcontroller. If you enjoyed this video, show it by clicking like and sharing it. Subscribe to my channel to get similar content in the future. If you want to get a taste of how I feel when I build my projects from scratch, you can get this custom PCB of my design and attempt to build this cool 3D 7-segment NeoPixel display. The link is in the description below. There you will also find corresponding STL files for printing 3D components. I will see you guys in my next video. Ciao.